Good day class. We will understand three-phase power with this week's series of video lectures. In this lecture, we will figure out how to represent parameters in three-phase. We will first describe a way to measure voltage and current in three-phase systems, then differentiate between line and phase voltages, and finally identify different three-phase connections. To be able to calculate the power, energy, etc. for an electrical system, we need to be able to measure the basic two parameters that are voltage and current. How do we achieve that in a three-phase balanced system? We would need to measure the source voltage either at VA per phase, or we may need to measure the load voltage V load. But the issue is that we cannot access the per phase part of the source that is inside a sealed machine, while the same can be said for the three-phase load, which may be something like a three-phase induction motor. So, where do we measure the voltages and currents now? The only available section is between the lines that connect the source to the load. We can measure the voltages across lines AB, BC or CA. These voltages are called line voltages. Now, if we can only measure the line voltages in a three-phase system, we need to be able to derive the phase values from the measured line values. Let us assume that we measure the line voltages between phases A and B. This gives us voltage VAB, which is drawn as follows with respect to the individual phases. The phase voltage VB is the same as the phase VA at an angle of minus 120 degrees. Thus, we can express VAB as VA plus minus VB. VB is VA at an angle of minus 120 degrees. This is clear from the phasor diagram as well. Evaluating this, we get VAB is equal to root 3 times VA at an angle of 30 degrees. Similarly, we can derive VBC as root 3 times VB at an angle of 30 degrees and VCA as root 3 times VC at an angle of 30 degrees. Thus, we get line voltages with respect to the phase voltages. We get the line voltages with respect to the phase voltages. We can conversely express the line voltage and phase voltage relationship as magnitude of voltage of phase A is equal to line voltage VAB divided by root 3. The voltage of phase B is the line voltage VBC divided by root 3, and magnitude of voltage VC is equal to magnitude of VCA divided by root 3. We can get a generic relationship for this type of three-phase connection, that the magnitude of the phase voltage is the line voltage divided by root 3. The type of source and load connection here resemble a Y or a star. For a star connection, phase current is equal to the line current, while the phase voltage is the line voltage divided by root 3. We looked at the Y or star type connection. There is another type of connection called the delta connection. The loads may be connected here in the form of a delta. Here it is evident from looking at the circuit that the line voltage VCA is the same as the phase voltage, which is also VCA. But we do not know what is the phase current. Since we can only measure the line currents, we need to find an expression that represents the phase currents with respect to the line currents. These two types of connections apply to both three-phase voltage sources as well as three-phase loads. Let us try to derive the expression for the phase current with respect to the line current in the case of a delta connected load. Applying KVL at the junction A, we get IAB is equal to IA plus ICA, or I can write it as IA is equal to IAB minus ICA. Let us assume the loads are lagging in nature with a power factor angle of theta. We can draw the phasor for three-phase voltage and current as follows. We can find out IA as IAB plus minus ICA. This gives us a value of IA as root 3 times IAB at an angle of minus 30 degrees. Similarly, we can say that IB and IC are root 3 times IBC and ICA at an angle of minus 30 degrees respectively. We can thus conclude that the line current is root 3 times the phase current, or the phase current is the line current divided by root 3. In this lecture, we understood how to measure voltages and currents in a three-phase system, differentiated between line values and phase values, and looked at different connections for three-phase systems. We also derived the line and the phase relationships for Y and delta systems as follows. For a Y-connected system, the phase voltage is the line voltage divided by √3, while the phase current is the same as the line current, while for a delta-connected system, the phase current is equal to the line current divided by √3, while the line voltage is the same as the phase voltage. Thank you.